So this is problem 1. In this problem we've got a weather balloon which is at 1 atmosphere. So the initial pressure is 1 atmosphere and a temperature of 22 degrees C. So the initial temperature is 22 degrees C. Now we'll actually need this in kelvins. So this is equal to 22 plus 273.15, which is equal to 295.15 kelvins. And the initial volume is equal to 3.47 meters cubed. So it then goes up to an elevation of 6.5 kilometers, and the atmospheric pressure drops down to 0.475 atmospheres. The temperature drops down to minus 48 degrees C, which again we'll need to convert that to kelvins. So to convert it to kelvins we do minus 48, sorry, there's no point there, so that's minus 48 plus 273.15, which gives us a final temperature of 225.15 kelvins. And we're asked what is the gas volume now, so we need the final volume of the gas. So to answer this one we'll need to use our ideal gas law. We've got PV is equal to nRT. Now nR is not changing, so we can rearrange this and write PV on T is equal to nR, which isn't changing, so this is constant. So because that's constant, we've got the initial pressure times the initial volume over the initial temperature is equal to the final volume times, the final pressure times the final volume over the final temperature. And we're trying to get the final volume, so the final volume is equal to the final temperature over the initial temperature times the initial pressure over the final pressure times the initial volume. Okay, so now we've got all these values, so we can substitute in. Now with the pressure, if you want, you can convert it to SI units. But when we convert it to SI units, we're literally timesing it by 1.01 times 10 to the 5 pascals. And we do the same thing to the bottom. So this is a common factor. So we don't actually need to convert the pressures. We do need to convert the temperatures because we convert the temperatures through an additive factor, so this doesn't cancel out like it does for the pressures. Okay, so the final temperature is 225.15, the initial temperature 295.15, the initial pressure was 1, the final pressure was 0.475, and the initial volume was equal to 3.47. Okay, so solving this, I end up with 5.57 meters cubed as the volume of the gas at that height. So even though the temperatures dropped, the pressures also dropped, so it has expanded. Okay, problem 2. So in this problem, we have hydrogen molecules. So their mass is equal to 3.3 times 10 to the minus 24 grams. So let's put that into kilograms. So this is equal to 3.3 times 10 to the minus 27 kilograms. And we have 1 times 10 to the 23 of these molecules, and they're striking a wall. We have the area of the wall is equal to 2 centimeters squared, which if we want to convert into meters squared, we have to times it by 10 to the minus 2 squared. So to get from centimeters to meters, we divide by 100, which is what timesing by 10 to the minus 2 is. To get from centimeters squared to meters squared, we need to square that. So this is equal to, sorry, that's a 2, not a 3. 2 times 10 to the minus 4 meters squared. And they're striking it at an angle of 55 degrees to the normal. Okay, so here's our wall, and we're striking it at an angle of 55 degrees like that. And they're moving with a speed v of 1.0 times 10 to the 5 centimeters per second, which if we want to convert it into meters per second, we'd have to divide by 100. So this is equal to 1 times 10 to the 3 meters per second. And the question is, what's the pressure? Okay, so we know that pressure is equal to force over area. We've got the area here, so we need to calculate the force. So to find the force, we'll need to go back to mechanics and use impulse. Impulse is equal to the force times the time, which is equal to the change in momentum, which is equal to the mass times the change in velocity. Now, if we consider this particle being reflected off the wall here, it's reflected back up at the same angle. So in the vertical direction, the change in velocity vertically is equal to 0, and all the change in velocity is in the horizontal direction. So if we break this velocity up into a horizontal component, this is the adjacent side, so it's going to be the horizontal velocity will be equal to v cos theta, and the final velocity is equal and opposite the initial velocity. So this is equal to m, well, let's call it x rather than horizontal, that's more normal, vx final minus vx initial. And so we've got that our force is equal to m. Now these have the same magnitude in opposite directions, so we can say that's 2 vx initial, or we could say vx final if we wanted, over time. And so now what we can do is substitute this into here. So we've got that our pressure is equal to 2 times the mass times the initial component in the x direction over the time over the area. Okay, and now we have everything, so we can substitute in. So we've got 2 times 3.3 times 10 to the minus 27 times the velocity, which is 1 times 10 to the 3, and then it's the x component, so it's times cos 55 divided by the time, this is in 1 second, and the area, which is equal to 2 times 10 to the minus 4 meters squared. So solving that on the calculator, we end up with 1.893 times 10 to the minus 20, and that is per molecule. But we in fact have 1 times 10 to the 23 molecules, so we need to multiply these two together to get the total pressure. So the pressure is equal to 1.9 times 10 to the 3 pascals. Okay, so this is problem 3. So we've got a tank which contains 315 grams of ammonium, so that's NH3. The molar mass of ammonium, we've got the nitrogen, which is equal to 14.007 grams per mole, plus 3 times the hydrogen, which is 1.008 grams per mole. So this is equal to 17.031 grams per mole. And we're told that it's at a pressure of 1.35 times 10 to the 6 pascals, and at a temperature of 77.0 degrees Celsius. And first of all, we're asked what's the volume of the tank. So we're going to need to use our ideal gas law. PV is equal to nRT. We can rearrange this. We've got V is equal to nRT on P. So we need to know the number of moles. We've got the molar mass. So the number of moles is equal to our mass over our molar mass. So it's 315 grams at 17.031 grams per mole. And so solving this, we get 18.50 moles. Okay, so now we have everything that we can substitute in here. So we've got N is equal to 18.50, R is equal to 8.314, T we've got 273.15 plus 77, over the pressure, which is equal to 1.35 times 10 to the 6. So it was important to convert from degrees Celsius to kelvins, which is why I added on the 273.15. Okay, and then we substitute that into the calculator and we end up with 0.0399 meters cubed, and I've given that to 3 significant figures. Okay, part B, we're then told that the tank is checked later. Now the temperature is equal to 22 degrees C and the pressure has dropped down to 8.68 times 10 to the 5 pascals, and we're asked how many grams of gas leaked out of the tank. Okay, so if we can work out how many moles left the tank, then we can work out how many grams. So let's use our ideal gas law to work out how many are left in the tank. So N is equal to PV over RT. We've got 8.68 times 10 to the 5. We know the volume of the tank now, it's 0.0399. R 8.314. And our new temperature is 22 degrees. So that's 22 plus 273.15. I can solve this and I end up with 14.12 moles. So this is how many moles are left in the tank. So the moles that leaked out, so N leaked, is going to be 18.50, my initial number of moles minus my final number of moles. And so that is around about 4.379 moles. We were asked for the mass in grams. So to get this from moles to grams, we just multiply it by the molar mass, which we calculated up here, 17.031 grams. And so this is equal to 74.6 grams. So that's how we solve that problem. Okay, so this is problem 4. And we're told that a sample of ideal gas goes through this cyclic process here, and that PB, which is here, is equal to 7.5 kilopascals. So that's 7,500 pascals. And PAC, which is here, is equal to 2.5 kilopascals. So that's 2,500 pascals. And we're told at point A here, the temperature at A is equal to 200 kelvins. So in part A, we're asked for the number of moles. So we'll need to use our ideal gas law. PV is equal to nRT. So N is equal to PV over RT. And now at point A, we know the pressure, we know the volume, and we know the temperature. So we'll work out all these things at point A. And so we've got 2,500 times 1 meter cubed over 8.314 times 200, and solving that on the calculator, I get 1.5 moles, and that's to 2 significant figures. And then in part B, it asks me what's the temperature of the gas at point B, so that's here. So the temperature at point B is going to be equal to, just rearranging our ideal gas law, PB/VB over NR. We're told what these are. The pressure is 7,500. The volume is 3. N we've just calculated, it was 1.5. R was 8.314. And so solving this on the calculator, I end up with 1,800 kelvins. C, I'm then asked for, well, what is the temperature of the gas at point C? So TC is equal to PCVC over NR. The pressure at C is the same as at A, it's 2,500 times 3 over N, which is 1.5 times 8.314. So solving this, a faster way to do this one is to realize that these two are the same, apart from we've gone from 7,500 to 2,500. So because the pressure is a third of the pressure at B and everything else is the same, our answer is also going to be a third, but we could have just put that into the calculator. So it's 600 kelvins at C. Problem 5. Okay, so in this problem we're asked to determine the average value of the translational kinetic energy of molecules of an ideal gas at 0 degrees and 100 degrees C. This is in part 1. So to do this we'll need to use our equation that the kinetic energy is equal to 3 over 2 times NKBT. Now this is the form that we use when we've just got a single molecule. When we've got moles, we use 3 over 2 nRT. And this will be familiar for you because it's very similar to our equation that the internal energy, which is all stored as kinetic energy, is equal to F over 2 nR delta T. But now we're just considering the translational kinetic energy. So F is equal to 3. Okay, so to do this one, we just do at 0 degrees C, we've got 3 over 2 times its 1 molecule Kb, that's equal to 1.381 times 10 to the minus 23. The temperature, that's 0 degrees C, which is 273.15 kelvins. And so solving this, I end up with 5.66 times 10 to the minus 21 joules. That's at 0 degrees C. At 100 degrees C, we've got 3 over 2 times 1 molecule times 1.381 times 10 to the minus 23 times, now 100 degrees C, that's 373.15. So solving that, I end up with 7.73 times 10 to the minus 21 joules. Now in part B is the same thing, but now it's for 1 mole. So one option would be just to multiply these answers by Avogadro's number, because that's how many molecules we have in a mole. The other option is to use this equation. So we've got 3 over 2 times 1 mole times R, 8.314, times T, which is 273.15. Solving this, we have 3,410 joules, which is 3 sig figs given to. And then at 100 degrees C, we've got 3 over 2 times 1 times 8.314 times 373.15. And this is equal to 4,650 joules. And that again is to 3 sig fig. Okay, so that's how we solve that problem. So this is problem 6. In this problem, it's a mean free path problem. So we're going to need to make use of our equation for the mean free path, that the mean free path is equal to 1 over the square root of 2 times pi d squared times n on v. And in the question, we're told that our molecules are at 0.0 degrees C, which if we need to use this, we'll need it in kelvins. So 273.15 kelvins. Our pressure is equal to 1 atmosphere, which is equal to 1.01 times 10 to the 5 pascals. We're also given the mean free path, so we're told that this is equal to 0.80 times 10 to the minus 5 centimeters. So to get it into SI units, we need to divide by 100. So this is equal to 0.80 times 10 to the minus 7 meters. And we're told that we're then given the number of molecules per centimeter cubed. So we're given N on V is equal to 2.7 times 10 to the 19, and that's molecules over centimeters cubed. Now what we want it is per meter cubed. Obviously in a meter cubed there's going to be a lot more molecules than in a centimeter cubed. So each centimeter, to convert it to per centimeter to per meter, we'd need to times by 100. But because it's cubed, we times by 100 cubed, so 10 to the 6. So we multiply this by 10 to the 6. So this is 2.7 times 10 to the 19 times 10 to the 6. That's molecules per meter cubed. Or we could write it as 2.7 times 10 to the 25 molecules per meter cubed. Okay, now what we're trying to find is the diameter of the molecules. So we can rearrange this, and we've got that the diameter squared is equal to 1 over the square root of 2 pi times lambda N on V. And so it turns out that we don't actually need to know the temperature and the pressure, because we don't need to calculate this V. We've already got N on V here and lambda. So now we can just substitute in. So it's 1 on root 2 times pi times lambda, which is 0.80 times 10 to the minus 7, times N on V, which is 2.7 times 10 to the 25. So solving this one, we end up with 1.042 times 10 to the minus 19. And this is meters squared. So then to find the diameter, we take the square root of this, and we end up with 3.2 times 10 to the minus 10 meters, or we could write this as 0.32 nanometers if we wanted, and we've given that to two significant figures. Now it's a good idea just to make sure that this makes sense. We've been asked to find the diameter of a molecule. We know atoms and molecules have lengths of the order of magnitudes of 10 to the minus 10 meters an angstrom. So this is the right order of magnitude. So we haven't made a mistake in this case. Okay, this is problem 7. So in this problem, this is initially a gas in an ice water bath, is in thermal equilibrium. So the initial temperature is going to be 0 degrees C. We know that because it's an ice water bath. So if both ice and water are in thermal equilibrium with each other, that happens at 0 degrees C at atmospheric pressures. And then here we've got boiling water. So the water, gas, and hot water are in thermal equilibrium with each other. So once this has been moved down here and allowed to come to thermal equilibrium, the final temperature is going to be 100 degrees C. So part A says, is the final temperature greater than, less than, or equal to the initial temperature? The final temperature is greater than the initial temperature because the final temperature is 100 degrees C and the initial temperature was 0 degrees C. Now in part B it says, is the final pressure greater than or equal to the initial pressure? Now this one can be a bit tricky, but we need to remember what is causing this pressure. This piston is absolutely free to move. So what's causing the pressure in here is the weight force of the piston itself acting downwards, and also we've got atmospheric pressure up here. So it's nothing to do with this ice water bath. When we move it into the boiling water, once again we've got the same atmospheric pressure acting on it, and we haven't changed the weight of the piston, so because pressure is equal to force over area, and it's got the same cross-sectional area and the same weight force acting on it, the pressure inside is going to be the same. So the final pressure is going to be equal to the initial pressure because we haven't changed what's causing that pressure. Okay, part C then says, is the final volume greater than, less than, or equal to the initial volume? Well, as it heats up, it's going to expand. So we've got that the final volume is greater than the initial volume. And then part D says, are your answers consistent with the ideal gas law, which is PV is equal to nRT? In this case, yes, because T is increased, N and R have stayed the same. We've got the same number of moles in there. Pressure's the same, so the volume's also increased. So this is increased and this is increased. So it's all fine with the ideal gas law. And then part E, imagine that instead of being free to move, the piston was fixed in place. Okay, so now if the piston's fixed in place, let's put in blue what's going to happen. Once again, the final temperature is going to be greater than the initial temperature because it will come to thermal equilibrium. Now in this case, because the piston's not free to move, the pressure isn't caused by the atmospheric pressure and the force from the weight of the piston. There's this isn't in equilibrium with the pressure inside, and so in this case we'll have that our final pressure is greater than our initial pressure because it would have wanted to move up but it couldn't, and now because it can't move up, the volume can't change, so the final volume has to be equal to the initial volume. So, and part D, once again this is consistent because in this case our pressure has gone up and our temperature has gone up, but our volume stayed the same and our number of moles have stayed the same. Okay, so this is problem 8. With this one, we've got a tyre, and it's the pressure in the tyre is measured with a gauge which compares it to atmospheric pressure. So we'll need to keep that in mind. So the initial volume of our tyre is equal to 1.64 times 10 to the minus 2 meters cubed. The initial temperature is equal to 0 degrees C, which is equal to 273.15 kelvins, and the initial pressure, and this is the gauge pressure, is equal to 165 kilopascals. So that's the gauge, but this gives us the pressure without including the atmospheric pressure. So the initial pressure, not gauge pressure, we have to add the 1 atmosphere on, and 1 atmosphere is equal to 101 kilopascals. So this is 165 kilopascals plus 101 kilopascals, and so this is equal to 266 kilopascals. Okay, now afterwards it heats up. The final temperature is equal to 27.0 degrees C, which is equal to 27 plus 273.15, which is equal to 300.15 kelvins. The final volume is equal to 1.67 times 10 to the minus 2 meters cubed, and the final pressure, well, that's what we're trying to find. Once we've got the final pressure, then we'll be able to work out the final gauge pressure. So we'll need to use our ideal gas law. PV is equal to nRT. In this case, we've got nR is equal to PV on T, and this is remaining constant. We're not changing the number of moles. So this tells us that the initial volume times the initial pressure over the initial temperature is equal to the final pressure times the final volume over the final temperature. And what we're trying to get is the final pressure, and that's equal to the final temperature over the initial temperature. That's just rearranging this to make this thing the subject, times the initial pressure over the, we'll have initial pressure, but we'll put that last. Let's do the volume first. Times the initial volume over the final volume times the initial pressure. So now what we can do is substitute in. So temperatures, it's important that they're in kelvins. So this is equal to 300.15 over 273.15. The volumes, the initial volume is equal to 1.64 times 10 to the minus 2. The final volume is equal to 1.67 times 10 to the minus 2. And then times the initial pressure, which is 266 kilopascals. So that's going to give our answer in kilopascals. So solving this on the calculator, we get 287 kilopascals. So that's the total pressure inside. To get the gauge pressure, it's 287 kilopascals minus 1 atmosphere, which is 287 minus 101 kilopascals. And so that is equal to 186 kilopascals as the gauge pressure.